Alrighty, so in this video we're going to take a look at hyperbolas and how to graph them. So first, let's look at this equation right here, and you'll notice that it actually looks very similar to the ellipse that we looked at in the last video, or several videos ago. So let's look at that ellipse equation first. So here's our ellipse. That equation was, sorry about that, that equation was 9x squared plus 16y squared equals 144. And this one, well, I'm going to tell you right now, it's a hyperbola. But what does doing that little sign flip do exactly? So let's think about this. What if I were to take this graph and just like what I did for the ellipse, I solved it for x. So I'll do that for the hyperbola. So I'll rewrite it, 9x squared equals 16y squared plus 144. If I want to get x alone, then I'm going to have to divide by 9 and then take the square root of both sides. So I'll have x squared equals 16y squared plus 144 over 9. And so x itself would be equal to plus or minus the square root of 16y squared plus 144 over 9. Why not take the square root of that 9 as well? And I'll get plus or minus, the square root of, 1/3 times the square root of 16y squared plus 144. If I do a similar thing to this equation, I'm going to kind of fast forward the steps, but you'll see it'll be very similar. Move the 16y squared to the other side, then divide by 9, and then take the square root. But since it's a positive 16y squared to start, it'll end up as 144 minus 16y squared. So this will end up with plus or minus 1/3 times the square root of 144 minus 16y squared. Sorry about that. Okay, so let's stick with the ellipse just to remind us what happened. Well, if I want to figure out what x could be, I need to figure out what y could be in this case. And since it's inside a square root, I need that inside to be non-negative. So what we did was I took 144 minus 16y squared. And I need that to be at least 0. If I do some rearranging, we get 144 is greater than or equal to y squared. 16y squared. If I divide everything by 16, this came out to be 9 is less than or equal to y squared. And we talked about how to deal with this inequality and taking the square root. But this essentially means that the absolute value of y is less than or equal to, let's not rearrange order. 3 is bigger than or equal to the absolute value of y. Okay, which would mean that our y values are stuck between 3 and -3. If we come back over here to the hyperbola side, well, I still need the inside of that square root to be non-negative. And so I'll still start with the same setup. 16y squared plus 144 is at least 0. And now we can actually do something a little bit more clever than just kind of going about it, although there's nothing wrong with that. If you notice here, we need the inside of the square root to be greater than 0. If you look at this 144 chunk, well, 144 is already a positive number. And 16y squared, no matter what y value you plug into it, when you square it, it's going to be positive. And so this is, unless it's 0, and then in which case you'll get 0. So this piece is already positive or 0. And if you take a positive number and add to it nothing, or another positive number, it's already going to be bigger than 0. And so from here, we can just kind of fast forward this step and with a little bit of logic say that y can be any real number. And so our range, well, that would be our range. For the hyperbola. If you come back over here into the ellipse, remember that our range was very limited in that it was only between 3 and -3, or absolute value of y is less than 3. So that's already one difference that that little negative sign makes for the hyperbola when compared to the ellipse. Okay, so we have the range of our ellipse. Let us find the domain. And if you remember when, hyperbola. We have the range of our hyperbola, so let's find its domain. If you remember the picture of what a hyperbola looks like, you might be able to figure out that the domain should not be all real numbers if the range is all real numbers. And I'll let you kind of play with that picture in your head, but let's take a look at it here. So our original equation, if I remember, was 9x squared minus 16y squared equals 144. While we're here, if we remember, the domain of this ellipse was, I'm not going to show the whole step, or all the steps, but I believe x was between plus or minus 4. Okay, and I'm just putting that there to compare with our hyperbola. Now, let us now solve for y and then see what x could be. If you remember from before, I was able to figure out what y was by solving for x first and then looking inside the square root, inside that radical. So let's do that here. So negative 16y squared is equal to 144 minus 9x squared. I'll divide everything by negative 16. So when I'm dividing by negative 16, that will flip all the signs. So that'll be 9x squared minus 144 over 16. And now I can take the square root. So I'll leave with y equals plus or minus the square root of, 1/4 times the square root of 9x squared minus 144. All right, I fast forward to a little bit of the arithmetic, but hopefully this checks out with you. Now, once again, let us look inside. And I know that 9x squared minus 144 greater than or equal to 0. So right off the bat, we can see that indeed I can't just plug in any old x value, because if the x value is not big enough, then you'll have a positive number minus a negative positive number minus a positive number. It could definitely create a negative number, in which case you wouldn't be able to take the square root of it. So we do need to check this. So I'll just move the 144 over. 9x squared is greater than or equal to 144. If I divide by 9, I'll get x squared is greater than or equal to 16. And just like before, be careful when dealing with this x squared in the absolute value. But if x squared comes out bigger than 16, then the number that you had to square must have been bigger than 4 in magnitude. And the way we would denote that is that the absolute value of x is bigger than or equal to 4. Or in other words, our domain is between, if it's bigger than or equal to 4, let's look at a little number line here. Here's 0, here's 4, negative 4. Those 2 points have absolute value equal to 4. But if I want a greater absolute value, you would go farther away from 0. And so that's where your x lives. So either x is less than, it's a little not nice, less than negative 4, or x is greater than, positive 4. And that would be your domain. So take a look at our domain and range for the hyperbola. Sorry, just getting a little bit messy. This is our hyperbola, hype on this side, and then the ellipse over here. So now that we know what this hyperbola, or the domain and range of this hyperbola, how the heck do I actually graph it? Now let's take a look at this. So we know the ellipse. If I was to draw this one, we have its center, which was at 0, 0. It went out 3 and 4. So here's 4, and a little slightly less than that. There's 3 and negative 3. This is really messy, but it looks something like that. A hyperbola is a little bit harder to draw. So we know, and I'll let you kind of go with the assertion that, even though we haven't quite shown it yet, that this one would also be centered at 0, 0, just like an ellipse. But what would that mean? Well, our range is all real numbers, remember. So that doesn't really help me, but I do know that my domain is outside plus or minus 4. So I'm going to draw this kind of small here. So here's 4, and here's negative 4. And remember that our hyperbola either looks like this or it looks like this. So this one's going to look like so somehow. Something like that. And the reason I know that is because if it was the other way, like I'm going to show in green here, then this would have a domain of all real numbers and a non-infinite range. But that's not the case for ours here. Remember that our range is y is all real numbers, and my domain is that x, absolute value of x, is bigger than or equal to 4. You need a little bit more for this hyperbola though, and here's also the centers at 0, 0. The question is, how wide are these kind of parabola-esque shapes? They're not exactly parabolas, remember, but they're parabola-esque. So, for example, how do I know it's that red one and not something like this green one? It could, for all I know, it could be like that, really skinny. Or they might be like really fat, like that. We're going to take one more look at the graph here. So, or the equation rather. So I want to take a look at this. All right, so I'm going to bring that down here. So remember that this is the exact same thing as the equation we started with. It's just been rearranged, rewritten. So y is equal to plus or minus 1/4 times the square root of 9x squared minus 144. Okay, if we think about this, and we've talked about the idea of asymptotes in the class months ago, right? But my question to you is the same question as before. What happens when x is big? And when we mean big, we mean like really big, for lack of a better term, right? If I look inside, start off by looking inside here. Once you have 9x squared minus 144, the 9x squared is way, way bigger than the 144. And so since 9x squared, and when I say it's bigger, it's like a lot bigger than 144, again, at big x values. What does that mean? Is that, well, this graph essentially looks just like plus or minus 1/4 the square root of 9x squared, because that 144 is negligible, again, in the long run. Not exactly equals to, because obviously 10 bajillion minus 144 is not equal to just 10 bajillion, but it's very, very close in the grand scheme of things. So what does this actually look like? If you clean up the square root, this is actually going to be plus or minus the square root of, the square root of 9x squared would be 3x. And so it would be 3 over 4x. Take a minute, pause there, and convince yourself that that works out. But once you've done that, what is this graph? Well, one, it's the asymptotes, because this whole idea here, this question, tells you to find asymptotes. Asymptotes, or this process rather. And this graph right here, y equals 3/4 x, that's a line. And y equals negative 3/4 x is a line. So really, your asymptotes are y equals plus or minus 3/4 x. And so now, let's see, I have a slope here, 3/4. Let's see, that might have a slope of, well, I'm just going to draw it in because it works out for me, but 3/4 is going to be less than 1, so it'll look something like that, and also something like that. And once you have these asymptotes drawn in, it helps you draw in your hyperbola a little bit more precise, because you know to start off at where the domain or range starts, and as you leave that kind of vertex of that quote-unquote parabola, it's getting closer and closer to those asymptotes. You see here in red. Okay, so that was obviously a very long process, and hopefully that makes sense as to how I was able to rearrange the original equation to figure out where the domain and range is, and also figure out our little asymptotes. Okay, but how could I do this maybe a little bit more efficiently. Last thing here. Y equals, so sorry, I'm gonna start from the very beginning. 9x squared minus 16y squared equals 144. Once I have this, if you remember from the ellipse video, we can actually see all the features of the ellipse if I can get this equation to equal 1. So I'll do that again by dividing by 144. So if I divide by 144, just do it like that, then I'll get, in this case, x squared over 16 minus y squared over 9, equals 1. And just like before, I'm going to rewrite the x squared over 16 as x over 4 squared minus y over 3 squared equals 1. And just like in the hyperbola or in the ellipse video, we can see these features here. I'll zoom out a little bit so we can all see. Where does this 4 come in? This 4, well, shows up right here in our distance from the center, and it also shows up in our slope. The 3 for the y doesn't quite show up as obviously in the graph, but what that's really important for, circle in blue, highlight in blue, it helps get you the other piece of that slope for your asymptotes. And so we'll still call these the x and y radii, rx, ry, but they just have slightly different meaning than, say, an ellipse. Okay, so there's definitely more to talk about. So the question is, we'll do more examples of this in the next video, and also figure out, how do I know which way the hyperbola even opens up? Okay, so keep an eye out for the next video.